Powers and polynomials. This is example test 2.1, and we're going to be looking at y equals x to the n, where n is a natural number, that's the counting numbers 1, 2, 3, 4, 5 and so on, or n is equal to -1, or n is equal to a half. So let's start with n equals 1. If n equals 1, then we just have y equals x, and this is a straight line, and you should know this straight line. It has a gradient of 1, and it goes through the origin. Now I'm going to start by looking at the odd powers. So the next one I'm going to look at is n is 3, which would give us y is x cubed. Now that looks like this, and we're going to look at some of the features of this a bit later in the example. So when we move to n equals 5, so y is x to the 5, that looks like this, and you'll note it's very similar to the x cubed. When n equals 7, we get y equals x to the 7, and you'll notice there's similar features again. And we're going to discuss some of these things. So if we look at the curves n equals 3, n equals 5, and n equals 7. So they all go instantaneously flat at the origin. Perhaps that's not quite clear at this scale of doing things, but we're going to look more closely at that shortly. This is a special type of point known as a horizontal point of inflection. You'll notice the gradient is positive here, then if it goes 0 here, it's positive again afterwards. They all go through -1, -1, and 1, 1, in addition to all going through 0, 0. It's difficult to tell on this scale, but as n increases, the curves become increasingly flat in the vicinity of the horizontal point of inflection. So that's at 0, 0, where it goes flat. Away from the horizontal point of inflection, the curves become increasingly steep as n increases. Now that should be clear if you just look at the graphs around here, but on the next slide that will be even clearer. All of the curves show that these are odd functions, so just remember that because it's important later in the course. Now, a formal way of saying that the graph goes off the top here is to say that y tends to infinity as x tends to infinity. So as x gets bigger, we're saying that y gets bigger, but the important thing is y is positive and bigger when x is positive and bigger. Down here, y goes to negative infinity, it goes off the bottom of the graph as x becomes more negative, going this way. And that's true on the others as well. Now, looking at this on a different scale, notice that we've just gone from -1 to 1. So this is the point 1, 1 here. The point -1, -1 is here on all three of these graphs. And here we have x cubed, x to the 5, and x to the 7. Now we can see this increasing flatness that we talked about on this type of scale. But also, if you look here, this is less steep than this is, and this is steeper again. So on this scale we can see the increase in flatness near the horizontal point of inflection at 0, 0. And we can also see how the curve goes more steeply through 1, 1 as n increases. Now let's look at some of the even powers. So if n is 2, y is x squared, and this is a curve you should know very well. If n is 4, y is equal to x to the 4, and that looks like this. Notice there are similarities, but look at the origin, and also look at how steep it is up the sides. And when n is 6, y is x to the 6, we get this. Look at the curves for n is 2, n is 4, and n is 6. They all have a minimum point at the origin. They all go through the points 0, 0, -1, 1, and 1, 1. It's difficult to see on this scale, but as n increases, the curve becomes flatter near the minimum point. I think we can see that a little bit even on this scale, but let's zoom in on that. As n increases, the curves become steeper away from the minimum point, and we can tell that on this scale. Note here that y tends to infinity as x tends to infinity. So as x becomes large and positive, the graph goes off at the top of the page. But y also tends to infinity as x tends to negative infinity. So as x gets large and negative, the graph goes off the top of the page. And that's the same for all of the graphs. So here they are zoomed in on just a unit square, so from -1 to 1 on both axes. On this scale we can see the increase in flatness near the minimum point at 0, 0 as we go from x squared across to x to the 6. If we look here at the point 1, 1, we can see how the curve goes more steeply through 1, 1 as n increases. Now it's worth mentioning here that all of these powers are even, and these are even functions, something we need to know about later in the course. Basically, an even function is symmetrical with the y-axis as a mirror line. Now let's look at n equals -1. We've seen this graph before. It looks like this. Let's look at some of the features of this. So if we look here and here, the x-axis is a horizontal asymptote. That means the curve gets closer and closer and closer to the line, but never actually gets there. The y-axis is a vertical asymptote. Y tends to 0 from below as x tends to negative infinity. So the curve here is coming up towards the axis but never gets there. Over here, y tends to 0 from above, that's what this little plus means, as x tends to infinity. So the curve comes down to the x-axis from above. Y tends to infinity as x tends to 0 from above. So when x is small and positive, y is going to be very large and positive. Y tends to negative infinity, so it's going off the bottom of the graph, as x tends to 0 from below. This is the graph of y equals x to the -1 if n is -1, or we can write that as y equals 1 over x. Finally, we have n equals a half, so that's y equals x to the half, which can be written as the square root of x, and the graph looks like this. The curve originates at 0, 0. It just simply starts there. You can't take the square root of negative numbers, so there's no part of the curve over to the left of the y-axis. Although the curve is becoming less steep, and we can see that quite clearly, as it moves to the right, y still gets bigger as x gets bigger. So we can say that y tends to infinity as x tends to infinity.